Hello my friend, welcome back to You Can Do TV channel. The construction of the Semmering Base Tunnel involves the creation of two shafts, each 100 meters deep. These shafts, essential for the tunnel's development, are being built within a tight schedule of just 6 months. One shaft has a diameter of 14 meters, while the other measures 8 meters across. Precision and efficiency are critical to meet the planned construction timeline. Excavation progresses at an average rate of 1 meter per day using advanced drilling and blasting techniques. The process demands strict adherence to safety standards, ensuring both worker protection and structural integrity. Extreme temperatures, sometimes reaching as low as -20 degrees Celsius, pose additional challenges to both personnel and machinery. However, specialized equipment and experienced engineers mitigate these difficulties. The project employs cutting-edge technology and custom-built machinery for heavy-duty operations. A specialized shaft transport system, designed to handle equipment weighing up to 40 tons, is in use to facilitate the construction. By the spring, this equipment was fully integrated into one of the Semmering shafts, optimizing workflow efficiency. The expertise of the construction team extends beyond shaft excavation. With a reputation for innovation and excellence, the company leading this project is internationally recognized for mastering complex underground construction techniques. The Shaft Boring Roadheader, SBR, is an advanced machine designed for the efficient and safe excavation of deep blind shafts, reaching depths of up to 1,000 meters in various rock formations. It combines the vertical shaft sinking machine for the lower section and elements of hard rock tunnel boring machines for the upper working decks. Suspended by ropes and controlled from the surface, the SBR uses a cutting drum to loosen rock in a precise star pattern, minimizing overbreak. The mechanized excavation process enhances safety by eliminating the need for personnel in hazardous zones, while a pneumatic mucking system efficiently removes excavated material. The West Gate Tunnel project involves constructing twin tunnels beneath Yarraville, Melbourne, spanning over 6 kilometers. The process begins with the assembly and deployment of two custom-designed tunnel boring machines, TBMs, Bella and Vita, measuring 15.6 meters in diameter. These TBMs excavate rock and soil while simultaneously installing precast concrete segments produced in Benalla, forming the tunnel walls. Excavated material, totaling 1.5 million cubic meters, is transported via a conveyor system to a tunneling hub, mixed into a paste, and safely disposed of at a facility in Bulla. Trucks used for transport follow strict EPA guidelines. Once excavation is complete, the tunnels are fitted with road decks, lane markings, and freeway management systems. Upon completion, the project will provide a vital alternative route, enhancing traffic flow and connectivity for Melbourne's western suburbs. The construction of the Crossrail tunnels involved a series of highly coordinated phases to create a new underground rail network beneath London. The process began with extensive site preparations, including the excavation of access shafts and the assembly of tunnel boring machines, TBMs. These massive machines, each weighing 1,000 tons, were lowered into position and systematically advanced through the ground, carving out the tunnel paths. As the TBMs progressed, precast concrete tunnel segments were installed to form the tunnel lining, ensuring structural stability. The excavation process was supported by continuous monitoring and reinforcement to maintain safety and precision. In parallel, underground station tunnels were excavated, requiring careful engineering to integrate with existing infrastructure. Following tunnel completion, work transitioned to fitting out the tunnels with essential rail systems. This phase included the installation of tracks, electrical systems, ventilation, and communication networks. Stations were constructed and equipped with platforms, escalators, and passenger facilities. Testing and commissioning followed to ensure all systems operated efficiently before the rail service launch. The completed network will enhance London's transport capacity, connecting key locations with a modern, high-speed rail system. The Sandvik UJ440 mobile jaw crusher is a heavy-duty machine designed for high-performance crushing in various applications. It is built on a fully tracked chassis, ensuring mobility and stability across different terrains. Equipped with an advanced control system, the UJ440 continuously monitors and optimizes its operation, ensuring efficiency and reliability in all working conditions. The machine features a powerful jaw crusher that processes a wide range of materials, including quarried rock, aggregates, and demolition waste. Its intelligent onboard system allows for automatic adjustments, reducing downtime and increasing productivity. The UJ440 is well suited for surface mining, construction material recycling, and aggregate production, making it a versatile choice for demanding industries. Designed for durability, the UJ440 operates efficiently in extreme climates, delivering consistent results year after year. Its robust construction and user-friendly controls make it easy to operate while minimizing maintenance requirements. The combination of mobility, automation, and high crushing capacity ensures that the UJ440 provides a cost-effective and reliable solution for various crushing needs. Roller compacted concrete, RCC, is a durable and cost-effective paving solution designed to withstand heavy traffic for decades. It is commonly used in distribution centers, intermodal yards, terminal projects, and long-lasting roadways. RCC is produced using the same essential ingredients as conventional concrete, aggregates, cement, and water, but in different proportions. The materials are loaded into a hopper and transported via a conveyor belt to a twin-shaft mobile concrete batch plant, which efficiently mixes the zero-slump concrete in high volumes. The mix is then loaded onto semi-end dump trucks and delivered to the job site, where a front-end loader fills a modified paver. Without the need for forms, the paver compacts the material into a smooth, dense surface. A roller further compacts the RCC to achieve the required strength. With ACEIT systems and power trowels, the process is completed with a broom finish, providing a polished, cost-effective alternative to conventional concrete. Brundage Bone Concrete Pumping successfully executed the 555 tower mat pour in Bellevue, Washington, for a 600-foot-tall commercial structure with a concrete core and steel frame. Due to limited street space, an innovative pumping strategy was developed over several years. Instead of placing traditional pump trucks with outriggers on the street, pumps were craned into the excavation, with 3 on the north side and 3 on the south side. This setup allowed 12 mixers to unload simultaneously, significantly improving efficiency. The pour achieved a rate of 700 cubic yards per hour, running flawlessly without downtime. Careful planning and execution ensured a smooth operation, maximizing productivity while maintaining pedestrian access. The Gameco C450 concrete cylinder finisher is a highly versatile and efficient machine designed for bridge decks, slabs, and large concrete surfaces. It incorporates a 3-point finishing system that ensures precision and consistency in concrete finishing. The hydraulic cylinder allows for controlled lowering of attachments, enhancing operational efficiency. Equipped with external vibration and pan vibrators, the C450 improves concrete consolidation, eliminating voids and ensuring a high-quality surface. Its pin-connected sections allow for quick setup and adaptability to various project requirements, with frame widths ranging from 12 feet (3.66 meters) to 104 feet (31.7 meters). The high-production screed, integrated into the C450, features a leading auger for efficient material strike-off, a finishing cylinder for compacting and smoothing, and a trailing screed with a unique vibratory system for final surface refinement. This system reduces labor costs, increases production speed, and supports 3D model finishing, making it ideal for large-scale projects. The construction of the A45 Talbrick ICERN involves multiple phases, with a particular focus on bridge concreting and the use of a cantilever-formed traveler. Following the installation of the prestressing tendons, preparations for the concreting process begin. The contractor submits a detailed concreting plan outlining workforce requirements and the sequential layering of concrete to ensure uniform load distribution on the advancing scaffolding system. To ensure structural integrity, concrete compaction is a crucial step. This is achieved primarily using immersion vibrators, which eliminate air pockets and prevent voids from forming within the structure. Approximately 350 cubic meters of concrete are poured during the deck concreting process. After the concrete has cured, additional prestressing tendons are tensioned, and the internal formwork of the deck is removed. Subsequently, the formwork for the roadway slab is installed and reinforced before another 400 cubic meters of concrete is poured. The cantilever form traveler, a specialized support framework, is then used for constructing the parapets. This structure is mounted beneath the cantilever arms of the superstructure, allowing for precise formwork installation. Once the parapets are completed, the traveler is repositioned using a side winch. The construction of the Tappan Zee Bridge replacement over the Hudson River was a major infrastructure project requiring extensive planning, engineering, and resources. The project utilized more than 300,000 cubic yards of concrete, 110,000 tons of fabricated steel, and nearly 7,000 prefabricated concrete deck panels. To support the structure, 50 miles of foundation piles were installed. Thousands of workers contributed to the effort, which included overcoming challenges such as weather delays and a crane collapse. The bridge was designed with future growth in mind, incorporating space for mass transit options. Funding was secured through multiple sources, including state funds, federal loans, and bonds. After construction, legal disputes arose regarding costs and structural concerns, but the bridge remains a critical transportation link. With a 100-year design lifespan, it is expected to serve millions of travelers each month while maintaining structural integrity and safety for generations to come. The replacement of the Liam Whalen Bridge was a crucial element of the Lewis Cross City construction project. The bridge, located on Fasaw Road in Cabra, required significant structural modifications to accommodate the new transport infrastructure. The project was carried out by Irish Rail in partnership with CISC and commenced in October. The first phase of the project involved the construction of new foundations and support structures necessary to sustain the new bridge deck. This preparatory work ensured that the subsequent steps of the replacement process could be executed efficiently and safely. The second phase entailed the construction of the new bridge deck. Rather than dismantling the existing structure first, the new deck was built adjacent to it on a temporary supporting platform. This method minimized disruptions and allowed for a seamless transition between the old and new structures. The temporary platform provided a stable base for the new deck while the existing deck remained operational. Once the new deck was completed, the existing bridge deck was carefully dismantled and removed. Following this, the new deck was maneuvered into its final position. This process required meticulous planning and execution to ensure the correct alignment and secure installation of the new bridge deck. Additionally, new abutments were installed to reinforce the bridge's overall stability and longevity. To facilitate the final installation phase, a 3-week road closure was implemented, allowing for uninterrupted work on the bridge. This closure was necessary to ensure the safety of both workers and the public while the new structure was being positioned and secured. The road was successfully reopened to traffic on the 26th of July, marking the completion of the bridge replacement process. In recognition of the bridge's historical significance, the Liam Whalen commemorative plaque was scheduled to be reinstated in the following weeks. The main span lowering of the new NY Bridge involved a highly complex and precise engineering process. The team faced the challenge of constructing massive main span pile caps, which serve as the foundation for the bridge's iconic towers. To achieve this, large forms, comparable in size to football fields, were carefully lowered into the Hudson River. The operation utilized SMU 330 heavy lifting jacks and post-tensioning strands to control the descent with extreme accuracy. Over 8 hours, the forms were lowered 9 feet while maintaining a precision of a quarter inch. Once positioned, they were filled with 14 feet of steel-reinforced concrete, marking a major milestone in the bridge's construction. The Sydney Metro, Western Sydney Airport, Station Boxes and Tunnelling, WSASBT, project is a crucial infrastructure initiative aimed at enhancing transport connectivity in Greater Western Sydney. Led by CPB contractors in joint venture with Gela, the project is being delivered for the NSW government to support the region's growing population and the development of the new Western Sydney International, Nancy Bird Walton, Airport. The project involves the design and construction of 9.8 kilometers of twin tunnels, along with the excavation of station boxes at key locations, including St. Mary's, Orchard Hills, Airport Terminal Station, and Aerotropolis Station. Additionally, service facilities will be constructed at Bringelly and Claremont Meadows. Construction commenced in 2020, following approvals from both the Australian and NSW governments. Major construction activities, including station excavations, were scheduled to begin in late 2022, with tunneling operations set to start in mid-2023. Once complete, the Sydney Metro WSASBT project will provide a vital transport link, reducing congestion and improving accessibility in Western Sydney. The initiative is also expected to generate more than 14,000 jobs, contributing significantly to the state and national economies. More information about the project can be accessed through the Sydney Metro website. Excavation and site preparation. During the blockade, 7,500 tons of material were excavated to create the required space for the bridge installation. This included the removal of old track components, ballast, and other obstructions. The excavation was conducted with precision to ensure that the site conditions matched engineering specifications, allowing for seamless placement of bridge components. 100,000 tons of stone were used to build temporary access roads and foundations, ensuring the stability of heavy equipment and materials throughout the operation. Given the scale of the project, proactive ownership and scalable learning strategies were applied to mitigate risks and enhance efficiency. Logistics planning covered component transport, site access management, and contingency plans for adverse weather conditions. Structural installation. The main structure of the bridge consisted of 2 primary steel beams, each weighing 107 tons. These beams were carefully transported and positioned using specialized lifting equipment. The bridge deck, measuring 40.5 meters in length, was assembled with over 1,300 individual components, including 6,000 bolts and 3,300 countersunk fittings to ensure structural integrity. To support the bridge, sill units weighing 50 tons each were positioned with extreme accuracy. The bridge installation had to be carried out despite challenging weather conditions, including wind gusts of up to 48.8 miles per hour. Skidding operation. A critical part of the process was the skidding operation, where the bridge was moved into its final position. The skid track measured 86 meters, providing a controlled pathway for the bridge movement. The skid operation, covering 20 meters in length, lasted 109 minutes and required meticulous alignment, as the bridge needed to be placed within a 17.5 mm tolerance over a 45.5 meter span. The process was carried out under a 72-hour blockade to minimize disruption, utilizing advanced engineering techniques and rigorous project management to ensure success. The installation of the Lincoln Eastern Bypass (LEB) rail bridge was a complex and meticulously planned operation, requiring extensive preparation and precise execution. Rail track installation and finalization. Once the bridge was positioned, work commenced on reinstalling the railway infrastructure. This included laying 800 tons of new ballast and placing 288 new sleepers to support the track system. Additional structural reinforcements were added to ensure the long-term durability of the bridge under heavy rail traffic. Throughout the process, 3,660 work hours were expended within the blockade period to complete the necessary track modifications and final checks. Open collaboration between various stakeholders ensured that all tasks were completed within the designated timeframe. The process began with a complete closure of the N08 section, allowing uninterrupted access for the construction teams. Specialized equipment and materials were mobilized to remove the old pavement, which had likely deteriorated due to heavy traffic and environmental factors. Once the existing surface was cleared, the groundwork for the new roadway was prepared, involving precise leveling and compaction to create a stable base. Modern asphalt mixtures, designed for durability and weather resistance, were then laid and compacted using advanced machinery to ensure a smooth, long-lasting finish. The roadway replacement process undertaken by ARJ Brienz-sur-Sea along the N08 highway under a full closure represents a significant engineering feat. This intensive project focused on replacing over 2 kilometers of roadway within a tight 48-hour window, targeting 2 key tunnels: the Seng Tunnel, 860 meters, and the Chubam Tunnel, 1,355 meters, located between Interlaken Ost and Brienz. The operation required planning, coordination, and execution to ensure minimal disruption while maintaining high safety and quality standards. The ARJ Brienz-sur-Sea Consortium, known for its expertise in infrastructure projects, managed the operation with remarkable efficiency. Over the 2 days, workers operated around the clock, leveraging the short time frame to complete the replacement across both tunnels. The Seng and Chubam tunnels, critical links in the regional transport network, now feature upgraded surfaces that enhance driving safety and comfort. This video showcasing this intensive roadway replacement highlights the scale and precision of the endeavor, offering a glimpse into the technical prowess and teamwork involved. Preparation and foundation. The process begins with the preparation of the tunnel floor. The tunnel invert is constructed to be as level as possible, considering the tunnel's curvature and lateral forces acting on the track. A precision-guided paving machine, assisted by tachometers, lays a concrete base layer with minimal deviation. This foundation must meet strict dimensional tolerances since it directly supports the track structure. Manufacturing and transport of track slabs. Before on-site installation, track slabs are prefabricated in a specialized facility. The production involves placing pre-tensioned reinforcement into molds, followed by the pouring of high-grade concrete, C45/55. Vibration techniques eliminate air pockets, ensuring a dense and uniform slab structure. The Katzenberg Tunnel, part of the Karlsruhe-Basel railway expansion, incorporates a slab track system to enable high-speed train travel at speeds of up to 250 km per hour. The installation process is highly precise and follows a meticulously planned sequence to ensure safety and performance. Once cured, each slab undergoes strict quality checks and is labeled with an identification code to ensure correct placement during installation. After quality verification, the slabs are transported to the tunnel. Each truck carries 3 slabs to the designated assembly point. The transportation process is synchronized with the tunnel's installation schedule to maintain a continuous workflow. Slab installation in the tunnel. The installation within the tunnel is carefully planned to minimize disruptions. The slabs are positioned using specialized lifting equipment and secured with alignment clamps to ensure correct positioning. The required tolerances for slab placement are extremely tight, often within 1 mm for both height and lateral positioning. Once in position, the slabs are permanently fixed in place using an undergrouting process. A specially formulated concrete is injected beneath the slabs, ensuring complete contact and eliminating any voids. Care is taken to prevent the slabs from floating during this process, preserving their precise alignment. Final adjustments and track fixing. After the undergrouting concrete has fully cured, longitudinal stability is ensured by tensioning the slabs with integrated locking mechanisms. This step prevents any movement under operational loads, creating a continuous and stable rail support system. With the slabs securely in place, the rail fastenings are installed. A temporary track is laid to facilitate the transport of long welded rails into the tunnel. These rails, typically 180 meters in length, are installed using specialized rail mounting equipment. The temporary track also allows for the installation of overhead power lines and other railway infrastructure. The completion of these steps results in a precisely aligned, stable, and maintenance-friendly track system capable of supporting high-speed railway operations safely and efficiently. The process begins with the start of track possession, where sections of the railway are temporarily closed for maintenance. Following this, the old track is removed, including rails, sleepers, and fastenings. Next, the existing ballast is extracted using specialized conveyor belt wagons and DHS wagons, efficiently removing approximately 150 cubic meters of material every 1.5 hours. The track renewal process for Rome's Metro Line A follows a structured sequence to ensure efficient replacement while minimizing service disruptions. The renewal involves the removal and replacement of 25 kilometers of track on the Anagnina-Ottaviano section, with work carried out during temporary nighttime track possessions. Once the old infrastructure is cleared, new track components are laid. Concrete sleepers replace the existing wooden sleepers, ensuring greater durability and stability. New ballast is then unloaded and distributed along the track bed. Ballast regulation follows, ensuring proper alignment and support for the new track structure. Subsequently, track tamping is performed to compact the ballast and secure the sleepers in place. This process enhances the stability and longevity of the renewed track. Track brushing is then conducted to remove excess ballast and debris, ensuring a clean and well-maintained railway. The process began with extensive planning and preparation. Engineers assessed the bridge, a road overpass spanning the railway, to determine the safest and most efficient demolition method. Given its urban location, the team likely implemented measures to protect nearby infrastructure, such as utilities, including a pipe mentioned as a constraint, roads, and the railway below. Temporary traffic diversions and pedestrian pathways were established to maintain local access during the work. Demolition itself involved heavy machinery, such as excavators and hydraulic breakers, to dismantle the concrete and steel structure. The bridge's position over the railway meant coordination with rail operators was essential to avoid operational interference, possibly requiring short line closures or night work. A notable challenge was maneuvering sections of the bridge around the pipe, which required careful edging forward to avoid damage. Debris was systematically cleared and removed from the site, ensuring the area was ready for the next phase. Safety was paramount throughout, with workers adhering to strict protocols to manage dust, noise, and structural stability. Once the old bridge was fully demolished, the site was leveled and prepared for the construction of the replacement bridge. The demolition of the Oldham Road Bridge in Ashton-under-Lyne was a carefully orchestrated process to remove the existing structure and pave the way for a new, higher bridge to accommodate railway electrification. This critical infrastructure project required precision to ensure safety, minimize disruption, and prepare the site for reconstruction as part of a broader initiative to enhance Northern England's rail network. The R20E ballast regulator is a high-performance machine designed to distribute and profile ballast efficiently on railway tracks. Equipped with one central plow and two lateral plows, it ensures precise ballast regulation and redistribution. The machine operates seamlessly in both directions, increasing productivity and reducing turnaround times. Its design allows compatibility with multiple track gauges, making it adaptable for various railway networks, including narrow and standard gauge systems. Additionally, it is well suited for tracks with limited axle load constraints. The compact and economic design of the R20E enhances its efficiency while maintaining high output. The regulator's independent running mode enables it to reach speeds of up to 80 km per hour, facilitating quick deployment to different work sites. Its advanced plowing system ensures optimal ballast distribution, improving track stability and alignment. The combination of precision, adaptability, and speed makes the R20E a reliable choice for maintaining and optimizing railway infrastructure. The process begins with a cut in operation, preparing the existing track for renewal. This is followed by the fastening removal unit, which systematically removes the old rail fastenings, allowing for the extraction of the worn-out rails. A dedicated fastening pickup unit collects and secures the removed fastenings for disposal or recycling. Once the old rails are detached, the working group moves forward with the removal of old sleepers. These worn-out sleepers are carefully lifted and taken away, making room for the installation of new sleepers. The ballast leveling process follows, where the ballast is evenly distributed and prepared to support the new sleepers. This ensures a stable and uniform foundation for the renewed track. The P95 is engineered to be both economical and environmentally friendly, incorporating modern technological advancements to enhance its output and flexibility. The machine operates through a series of meticulously coordinated steps, ensuring the seamless renewal of railway tracks. The next stage involves the precise laying of new sleepers. The machine accurately places the new sleepers in their designated positions, ensuring proper alignment. After the sleepers are in place, the new rails are inserted onto them, effectively forming the structure of the renewed track. Precision is crucial during this phase to maintain the track's correct alignment and stability. Once the new rails are in place, the final step is the insertion of clips to secure the rails to the sleepers. This process ensures that the track is firmly held together and is ready for use. The entire operation is executed with high precision, minimizing errors and ensuring long-lasting durability of the renewed track. The P95 track renewal train is equipped with various components, such as PMP1, PMP2, and P2R, which contribute to its high efficiency and accuracy. These components work in synchronization to optimize the renewal process, reducing downtime and labor costs. The machine's reliability and ease of maintenance further enhance its economic viability, making it a preferred choice for railway infrastructure projects. The track renewal train P95 is an advanced piece of railway maintenance equipment designed for efficiency, accuracy, and high performance. It operates as a mobile factory, capable of replacing old railway tracks while ensuring the new track maintains its initial geometry. By incorporating advanced automation and engineering, the P95 ensures that track renewal is conducted swiftly and with minimal disruption to railway operations. The seamless coordination between different units within the train enables continuous workflow, significantly reducing the time required for track replacement projects. The P95 is not only focused on performance but also on sustainability. Its design reduces material wastage and optimizes resource usage, making it an environmentally responsible choice for railway maintenance. The combination of high precision, efficiency, and eco-friendliness makes the P95 a standout solution for modern track renewal needs.